Welcome back to Lecture 2 of Foundation Maths for Chemistry. In Part 2 of Lecture 2, we're going to be working with algebra. Here, you will revise how to substitute numbers into formulae and expressions, work with indices, expand brackets and collect like terms. Then, you'll learn how to factorize algebraic expressions, generate formulae, and finally, change the subject of a formula. Let's begin with substituting numbers into formulae and expressions. Here, we will be using letters and expressions to stand for mathematical quantities. Sometimes you are told the numerical value of each letter. It is then possible to work out the value of the corresponding expression. Let's look at an example. Here we have x plus 3. That is an algebraic expression. If x has a value of 9, then x plus 3 has the value of 12, because 9 plus 3 is 12. Care must be taken when substituting given numbers into more intricate expressions. In particular, be careful with minus signs and squares, cubes, etc. Remember BIDMAS. You must do algebraic expressions in this order. So we work with anything in a bracket first. Then we do indices, otherwise known as powers, as we covered in the previous part of this lecture. Then we do division and multiplication together. You can do those two in either order, but call it BIDMAS. We do division first, then multiplication. Finally, you do addition and subtraction, and you also do those together. So it means you can do addition and subtraction in either order. But we write it as BIDMAS because it makes a word that we can pronounce. So remember, BIDMAS, brackets, indices, division, multiplication, addition, subtraction. Let's look at an example of substituting numbers into formulae and expressions. So if p equals 5, q equals 2, and r equals minus 4, work out the value of p by q minus 5r. So we've been told p is 5, so we put 5 here. We've been told q equals 2, so we substitute 2 here in for q. Minus 5 by r, which we're told is minus 4, so we put minus 4 in here. Then we make sure we follow the rules of BIDMAS. So are there any brackets? Well, there are, but we don't have to do anything in those brackets. This just tells us that this is a minus number. And as you can see, there's only the numbers in there, so we don't have to do anything with brackets. There are no indices or powers. Division, there's no division to be done. Multiplication, now there is multiplication to be done. So we do the 5 by 2 to give us the 10, and we do the 5 by minus 4, which gives us minus 20. Now remember the minus, and don't forget that. Then we move on to addition, which here technically there is addition, because 10 minus a minus number, we turn two lots of minuses next to each other into a plus. So then we can just do the 10 plus 20, and it gives us a final answer of 30. Carrying on with substituting numbers into formulae and expressions. Sometimes you need to substitute values into a formula rather than an expression. The only difference is that a formula contains an equal sign, so the final numerical answer can tell you the value of another algebraic letter. Let's look at an example to make that have more meaning. So the distance s travelled by a particle is given by the formula s equals ut plus a half at squared. So here we're told s is distance. Now some of you may know this equation. Here we have u, which is the initial speed of the particle. T is the time that we're looking at the distance being travelled over. And a is the acceleration. So we're told to work out the value of s, the distance travelled, when acceleration equals 9.8 and time equals 3.5, and u, the initial speed, is 2.4. So all we simply have to do is substitute these numbers into the equation. So u is 2.4, so we substitute in here 2.4. T is 3.5, so we substitute that in here and here, as you can see, for here and here. And A is 9.8, so we substitute that in here for here. Then we have to remember BIDMAS, brackets, indices, division, multiplication, addition, subtraction. So, are there any brackets? No, so we can move on. Are there any indices? Yes. This 3.5 is the power of 2, so we must tackle that first. So by doing that, we end up with this second line. Now, we return indices. Is there any division? No. Is there any multiplication? Yes. So then we must do the multiplication next. So 2.4 by 3.5 is 8.4, and a half by 9.8 by 12.25 is 60.025. Feel free to do that calculation on your calculator. Next, addition. Is there any addition? Yes. So we next do the addition to give us this number here. And then is there a subtraction? No, we've now finished the equation. Now, 68.425 is quite a clunky way of writing it, so I've written it as 68, which is two significant figures. Now let's move on to working with indices. Indices are used in algebra as a short notation when a quantity is multiplied by itself. In the previous section, you used x to the power of 2 to mean x by x. In a similar way, x to the power of 3 is a short way of writing x by x by x. The number 2 here, or 3 here, is a power, or index, as we previously discussed. Sometimes you will meet higher indices too. So here's an example of t by t by t by t by t, which is t to the power of 5. So all I mean by here by higher indices are numbers higher than 3. You have probably already met the idea of simplifying algebraic expressions using indices, which are powers such as squares or cubes, as we discussed before. So e.g., you may have been asked to simplify x squared by x cubed, or perhaps y to the power of 4 all by 3. The rules for simplifying such expressions are quite straightforward, but they can appear confusing at first, so you should practice in order to be able to apply them confidently and correctly. The rules for multiplication and division are as follows, much like we covered in the previous part of this lecture. So x to the power of a by x to the power of b equals x to the power of a plus b. Here's an example. X squared by x to the power of 5 is the same as writing x to the power of 2 plus 5, which is the same as writing x to the power of 7. So much like timesing, we add, divide, we subtract indices. So x to the power of a divided by x to the power of b equals x to the power of a minus b. Here's an example. X to the power of 6 divided by x to the power of 3 is the same as writing x to the power of 6 minus 3, which is the same as writing x to the power of 3. Sometimes the algebraic terms will have the whole number multiples in front of them. These are known as coefficients. If these are present, you simply multiply or divide the coefficients in the usual way, and then multiply or divide the algebraic terms as well. Now, that last sentence may not have made that much sense to you, so here we have an example of 4 to the power of x squared by 3 to the power of x to the power of 5. So we can simply times the 4 and 3 together and add the power of indices of the x's, so 2 plus 5 in this case, because we have squared to the power of 5. And that gives us 12 times by x to the power of 7, which is the same as writing 12 by x to the power of 7. Take care with an expression such as x cubed all squared. It does not simplify to x to the power of 5. This is because x cubed all squared means x cubed times by x cubed, which gives x to the power of 3 plus 3, in other words, x to the power of 6. So this gives us another rule for indices to add to these two that I've carried on from the previous slide. So here we have x to the power of a all to the power of n is the same as writing x to the power of a times by n. So here's an example. X to the power of 3 all to the power of 6 is the same as writing x to the power of 3 by 6. And 3 by 6 is 18, so it's the same as writing x to the power of 18. Expanding brackets. Here you will learn how to expand and simplify brackets. The instruction simplify tells you to collect together like terms where possible. So here's an example of simplifying. 3x plus 2y plus 9x minus 6y. Now we collect together the x's, so 3x plus 9x is 12x, and we collect together the y's, so 2y minus 6y is minus 4y, so therefore we simplify this expression to 12x minus 4y. Some algebraic expressions are written with brackets. It may be possible to expand the brackets, which means that you multiply them out and rewrite the result without brackets. Let's look at an example. Expand 2, open bracket, 4x plus 3, close bracket. Now, how do we go about doing that? Let's find out. So, 2, open bracket 4x, basically means 2 by 4x, so we can do 2 lots of 4x. And then we have plus 3, so we have 2 by plus 3, as written here. And then we can simplify these bits as 2 lots of 4x is 8x, and 2 by 3 is 6. So that's how you expand that simple bracket. Multiplying two brackets together. It is possible to expand the product of a pair of brackets multiplied together. There are several possible methods, all leading to the same end result. Now I'm going to talk you through some techniques to solve them. Smiles and eyebrows, FOIL, and a grid method. Now note, just find the method that's right for you and stick with that method. They all give equally valid answers. Now let's look at an example to understand these three different techniques that you can do. So here we have to expand and simplify 2x plus 5 by 4x minus 3. So the first method we call smiles and eyebrows. And that's just from the shape that we form here. So this number 1, 4 sections of this look a bit like eyebrows, 2 is a bit like a nose, and 3 is a bit like the smile. So we just follow these through in order. So we do this eyebrow first, 2x by 4x gives us the 8x squared. Then we do the number 2 here, that's 5 by 4x gives us plus 20x. Do number 3 of 2x by minus 3 to give us the minus 6x. And we do the fourth one here of plus 5 by minus 3 to give us the minus 15. Now, you could do this in any order you like, as long as you make sure you do every single one of them. I've just done this in this order to show you the ordering I was doing it. But you can do this 1, 2, 3, and 4 in any order you like, although typically you should write the answers with the highest powers first. So here, we have x to the power of 2, and then we have the lower power of x here, which is effectively x to the power of 1, and here effectively we have x to the power of 0, because that is the same as writing 1. But as long as you write the final answer in the order of decreasing powers, you can do these numbers in whichever order you like. Let's look at FOIL. Now FOIL is very, very similar to smiles and eyebrows, but instead of drawing out this sort of eyebrow and nose and smile section, we sort of do it in our head, remembering this acronym, FOIL. So F in FOIL stands for first, so that means do the first one numbers by each other inside the brackets. So here 2x to the first one and 4x to the first one. Then we do the outsides, so that's 2x by the minus 3. Then we do the inside, which is the 5 by the 4x. And then we do the last, so the last one in each bracket, 5 by the minus 3. So FOIL, first, 2x here, 4x here, outside, 2x minus 3, inside 5, 4x, last 5 minus 3. Both the FOIL and Smiles and eyebrow method are equally valid, and so is the grid method, if you do not like either the Smiles and eyebrows or the FOIL method. Now the grid method, we just write out each of the brackets across the top and the other one down the side. So 2x plus 5 across the top and the 4x minus 3 down the side here. And then you simply populate all these squares with timesing the row and the column together. So we have 2x by 4x for this box, which gives us 8x squared. This box here we have 2x by minus 3 to give us minus 6x. This box here we do plus 5 by 4x to give us 20. And this one here we do plus 5 by minus 3 to give us minus 15. And then we can write that all out in one line, collect together the similar expressions to simplify, and that gives us 8x squared plus 14x minus 15. So it's completely up to you which method you want to do, either Smiles and eyebrows, FOIL or grid method, but whichever method you find best, stick with that, and then you'll be easily able to expand and simplify brackets being multiplied together. Factorizing common factors. Sometimes it is desirable to apply the reverse of expanding brackets. This is known as factorizing. The idea is to take an expression that does not contain brackets and rewrite it as a kind of product of factors so that the brackets are required in the final answer. There are several different types of factorization. The simplest type of factorization is to extract a common factor. You examine the terms of the expression one at a time and look for the highest numerical and or algebraic factors of each term. So let's look at an example so that makes a little more sense. So here we're told to factorize 15x plus 3y. Now there are no algebraic common factors. However, we do know that there is a common factor in 15 and 3. So let's try and pull out the highest common factor, which we know of those two numbers is 3, because 15 is a multiple of 3. So if we pull that out, we can write 3 open bracket 5x, because we know 3 by 5 is 15. And if we did 3 by 5x, it gives 15x. And if we pull out the 3 from the y as well, it shows us that we just write y here, because 3 by y gives us 3y. Factorizing quadratic expressions. Earlier in this lecture, we practiced multiplying out the product of two brackets. It's possible to reverse this process in order to factorize some kinds of algebraic expressions known as quadratics. Let's look at an example. Here, we need to factorize x squared plus 7x plus 6. Now, there is a very systematic method to doing that. So we take the expression here that's being squared, we open a bracket and we write that expression there. And we close the bracket further down. We open another bracket and write that same expression here because it's squared, so we know this by this gives us squared, which is this number here. And we leave some space and we close the bracket. Then we need to determine what these signs are. Now, you look to determine that, you look at the last number. If it is a positive sign, we know that we can put positives in both of these. If this, however, is a negative, one of these should be a positive and one should be a negative. How do we know that? If you remember FOIL, the last multiplication would end up giving you this number here, and that would be this by this. Now, to give us a positive number, the only way of doing that, these both have to be positive. And to give us a negative number, one of these two would have to be negative, and simply write the second one to be negative, just to make the maths more simple. Now that we've determined that these are both positive, and these should both be x, we then need to figure out what the last numbers here could be. Now, the last multiplication of 6 by 1 here would work to give us 6, but it could also be 2 by 3, so that would give 6. So we don't know initially what these numbers should be. We have to figure out what those numbers should be by using this, knowing this number here in conjunction with this. Now, if it was 2 and 3, that would give us 5x, so we know it can't be that. 6 by 1 though would give us 7x, so therefore we know it should be 6 and 1. Factorising harder quadratic expressions. Suppose you need to factorise a quadratic such as 2x squared plus x minus 3. This is a little harder than previous examples. However, exactly the same methods are used, but there are more possibilities to consider because 2x squared can factorise as 2x in one bracket and x in the other. Let's look at an example. Factorise 2x squared plus x minus 3. So we do the same technique, we draw out the brackets. Now, there's only one way of getting 2, that's 2 times 1, so 1 must be 2x and the other one must be x. But we'll look at more complicated examples in the lecture if we have time. Then we must determine what the signs are. So this n number here is a negative, so we know we must have a positive and a negative sign. Then we need to figure out what the numbers at the end are. Now, what way can we make 3 by timesing two numbers together? Well, the only way is 3 times 1, so therefore we know this is 3 and this is 1. And that gives you how to then factorise this quadratic expression. Generating formulae. Formulae can be generated from information given in words. You may also generate them from information given by a diagram or even another formula. Let's look at an example. Here we're told a factory worker produces handbags by cutting and shaping rectangles of material. To make one bag, a rectangle of material p centimeters by q centimeters is needed. The factory finds that an area A of a material is just sufficient to make n bags. Obtain a formula for A in terms of P, Q, and N. Initially that might seem quite daunting, but let's work through a solution to see how to get the answer. The area required for one bag is found by multiplying P and Q together because we're told they're a rectangle. So therefore we know the area is just PQ. Now, for n bags, the area of material must be times by n, because for each extra bag we're getting, we need another PQ. So therefore, we can just times it by n. Thus, the answer for this, the area needed, is just the number of bags times by the area of the rectangle for each bag, which is just PQ. So A equals NPQ. Changing the subject of a formula. A formula usually has a single letter term on the left-hand side of the equal sign. This is called the subject of the formula. For example, the formula C equals 2 pi r has C as its subject. Sometimes you will need to rearrange the formula so that one of the other letters becomes the subject instead. Let's look at an example so that makes more sense. Make r the subject of C equals 2 pi r. Now you may recognize this equation as just the equation for the circumference of a circle. So, we want r to be the subject of this. So, we write out the original equation, C equals 2 pi r. We flip it round, so on the left-hand side instead we're looking at the algebraic expression that we want to understand, in this case r. So now we have 2 pi r equals c. Then we simply divide by the 2. So we can divide both sides by 2 to remove the 2 from the left-hand side to the right-hand side, as you can see here. C is now divided by 2. And then we simply finally divide by the pi to give us r equals c over 2 pi. Now remember not to do 2 divided by pi because it's this expression that's divided by pi, not the 2 itself. So that's why it's c over 2 lots of pi. That concludes this part of the lecture.